Hello, good afternoon and good morning for mostly all of you. This is Alberto Aguerri, and I wish that you stay safe and healthy. Today, I would like to introduce Natalia Bermejo. She's the presenter today, and she's an application specialist at Sensofar, and she's going to explain today how to apply the ISO 25178. So, Natalia, please.
Thank you very much for the introduction, Alberto. So welcome to this webinar about the ISO 25178. Thank you for having some time to attend. And right now I'm going to turn off my camera in order to avoid some audio and video issues of the connection, but I will turn it on again whenever the questions time comes, okay? So let's get started. So first of all, I would like to explain a little bit the agenda of this presentation. So I'm going to explain the company first, then we are going to talk about definition and how we acquire roughness, and which are those equipments that indeed can acquire roughness. So actually we're going to compare them, which are contact profiler versus optical profilers. And finally, we are going to talk about the ISO 25178, and especially we're going to mention the S, L, and F filters and the roughness parameters. So this is the staff of Sensofar in headquarters. And Sensofar is a company that was founded in Spain, in Terrassa, nearby Barcelona. And it is a spin-off out of the UPC, the Polytechnical University of Catalonia. So it was founded in 2001. So that means that we have near 20 years of experience in optical metrology. And the goal of this company is to design optical instrumentation that is going to be able to characterize micro and nanoscale surfaces. So because of that, we are able to provide solutions in a really wide range of fields, such as quality control, quality inspection, and R&D. So this is how headquarters in Spain looks like. So in there, which is in, again, Terrassa, Spain, we find production, R&D, marketing, and sales. But we also have another offices around the world. So actually we have 2 offices in Asia, one in Shanghai and another in Taipei. Then another one in Germany, Munich, and finally we will find one in Newington, USA. So in here, we can see some of the partners and customers that we have been working with. I apologize, we cannot show all of them because of confidential reasons. But for example, I would like to point out the NIST and the PTB because actually they have some relevance in terms of this webinar, which is the ISO 25178. So now let's go and start with the topic of today. So what is roughness? In here we have 3 different topographies, and actually those are topographies of intraocular lenses, but actually what we see here, it's the same topography with different filters applied. So the first topography on the left, it's without filters. The one in the center, we have removed the spherical shape of the lenses. And finally, the one in the right, we have removed not only the shape, but also those wavelengths that are middle-sized or waviness. So normally in metrology, we would say that we are going to calculate roughness out of the third one, but actually roughness can be calculated out of the three of these ones, because actually roughness, what it is a calculation on any data set that we are interested on. So surfaces, they are going to be really important in terms of the functionality of a surface. And actually, whenever we are in the nanometer and the micrometer scale, the surface is going to be a main point that it's going to define the functionality of this material. So for example, properties such as adhesion, cleaning, friction, mechanical wear, biological interaction, or contact resistance, they are going to be defined by this surface. And roughness is going to be a way to characterize and to understand better our materials. So in order to obtain it, we need 2 different things. The first thing we need is equipment that is going to record that roughness. And then we have an ISO that it's going to establish what we need to do with this data set and the calculations that we can do with that. So we have in the first instance the context stylus profiler, which is an equipment that is going to be able to record a profile out of the surface, and the ISO applied here, it's going to be the 4287. Then we have the 3D non-contact areal profilers, which actually are the ones that Sensofar is offering as a company. And those profilers are able to image an area within a surface. And in that case, the ISO that applies is the ISO 25178. So let's deep in a little bit on this equipment. The context stylus profiler, it works as you can see here in this GIF. So we have a tip that it's going to be touching the sample, and this tip is going to be moving up and down depending on the interaction, and that is the thing that we are going to sense, and thus obtain that profile. And then for the 3D non-optical areal profiler, what we're going to be able to image is the whole area by inserting some light and then capturing the reflection. So from this slide, we can see two main differences. The first difference is that with the context stylus profiler, we need to touch the sample, while with the 3D non-contact areal profiler, we don't need to do that. And also, the data set is completely different. From one, we obtain a profile, and from the other one, we obtain an area. So because they work, the approaches are completely different. The resolution is completely different as well. So in this case, the resolution is going to be at its first instant limited by the radius of the tip. But also the geometry and this angle here that you're seeing in this schematics is going to have an impact. So for example, you can see that in the schematics on the right, depending on the shapes that we find in the profiles, the stylus is going to be able, of course, of image it well, but in another cases, the stylus, because of its size, it's not going to be able to reach the trig stream. And also because of the way that this equipment works and the fact that it's touching the sample, we have two consequences out of that. The first consequence would be that we're going to damage the sample. And actually, we damage it because also the tip is made of a really harsh materials, which are sapphire and diamond. And as well, the stylus over some time is going to suffer from wear. So the radius of the initial stylus tip is going to be wider, and that is going to, for sure, impact in the resolution of that stylus profiler. As for the non-contact profiler, the resolution, because we are treating an area, it's going to be defined by two different things. So we have the resolution, the lateral resolution, that is going to be defined by the Rayleigh criteria. And then we have the system noise, but also we can call it vertical noise, which is going to be dependent on the technology. So for example, we have confocal that depending on the magnification, we will have from 1 to 100 nanometers of vertical resolution, while in interferometry, it's not going to depend on the magnification, but in the technology within interferometry that we are using. So it will depend if we use a coherence scanning interferometry or CSI, or phase shifting interferometry or PSI. So if you want to deep in this topic about technologies, optical technologies, I would encourage you to check our website and look for the webinar of optical technologies that was performed by our CTO, Roger Artigas. So in here, this is kind of an schematics that it's showing the different technologies that we have at Sensofar. And actually, if we start on the right, we have interferometry, which is going to be really a really good choice if we have sub-nanometer and nanometer features on the surface. Then if we have confocal and focus variation, we're going to be able to image very well nanoscale and microscale surfaces. And finally, for the fringe projection technology, which is in the newest equipment that we have, DSY, we're going to be able to image sub-millimeter features. So in here we can see overall resolutions of the stylus profiler and the different technologies that we have at Sensofar. And we can see clearly that the confocal and interferometry, the optical technologies, are pushing more the limits on resolution. So now let's go to the differences between contact and non-contact. So in order to understand the surface, contact profilers and non-contact profilers, they work completely different. The mindset is very different. So imagine the case that we want to understand the geography of the United States, and as an optical profiler, we would have the whole surface. But in the case of a stylus profiler, we would have different profiles. So here we could have profile A and profile B. But actually, imagine that we only perform the profile B. We would be missing the Appalachia in the Rocky Mountains. So this example is clearly showing how easy it is to leave important information behind when using a stylus profiler. Then also something interesting to take into consideration is that with an optical profiler, we can obtain the information that we obtain with an stylus. So first of all, we are going to, in order to do that, we are going to take an areal measurement. Then we are going to extract a series of profiles with a width that is exactly the same as the diameter of the tip that we are going to simulate. And then we're going to do a mean of those profiles. Afterwards, we're going to apply a morphological filter, which is going to simulate how it's seeing that profile as for a tip with a certain radius and a certain geometry. And finally, we will apply the ISO 4287. So of course, we will have the same information, but it's clear that it's going to be a loss of information by doing this. So another case that may be interesting to take into consideration would be to characterize a whole area. So for an optical profiler, it's going to be as easy as to obtain that area and then calculate the roughness parameters. So actually, for example, SA, one parameter, it's going to give all the information, it's going to comprehend all the information within the sample. Well, if we want to do this with a stylus profiler, we need to do as many profiles as we need in order to cover the whole surface. So in this case, we have done 100 profiles. Then for each of those profiles, we need to calculate the roughness parameters. Afterwards, we do a mean and a standard deviation, and then we would have characterized that surface. But if we have a look at the numbers here, we will see that the mean value and the standard deviation, we find that we have more than 30% of standard deviation comparing to the mean value. So this way to image or to characterize an area with a stylus profiler, it's not only time consuming, but also not really effective. So this is the question that we have been asked for many times. So actually, if RA and SA can be directly compared, and the answer is no, they cannot be compared directly for many reasons. First reason would be that the approaches are completely different. So the resolution of the two equipments and the data sets that we are going to obtain, a profile and an area, are completely different. Then also applying the same filter on one direction, the same Gaussian filter with the same cutoff, it's going to affect differently to one direction than to two direction. And that is something that we treat here. Well, it's treating here in this article. So if you want to understand better that statement, I would suggest you to check it out. And also, for example, taking into consideration one single point parameters, we will always find those bigger in areal measurements because the stylus is not going to be able to reach the trick stream in the surface. But wait, they cannot be directly compared, but they can be correlated. So actually, the ISO is giving us some different guidelines in order to do this correlation. So the first tip would be to apply the same filters, the same type, which would be Gaussian, and the same cutoff. then we would need the same size of measurement, meaning that the length of the profile needs to have the same length as the transversal axis of the area. Then we need to compare equivalent parameters. So because aerial measurements, we have another axis taken into consideration, we will have more parameters such as spatial parameters that are able to be calculated. But in order to do this correlation, for sure, we will need to find those parameters that are going to be found in the two data sets, in profiles and areas. And finally, of course, we are going to need to perform a high number of measurements in order to have enough statistical resemblance. And now let's go to the ISO 25178. So this would be a chronological axis in which is explaining briefly how metrology has been evolving through time. So at the beginning, metrology was using profiles in order to characterize the surfaces, because actually in the 1930s, the first stylus profiler was created. So that technology was the one used for characterizing surfaces, but then in the 1980s, the first interferometer was created. And that led to metrology to have a new step, because actually we were able to characterize surfaces with 3D data. And time passed by, companies such as Sensofar were created. And in 2002, different entities, institutions, and companies related to the optical metrology, they were reunited and tried to do a standardization of aerial measurements, that is the ISO 25178. So this ISO here, actually Sensofar is part of it, and actually this ISO, it has 7 different parts, but in this presentation we're going to go through part 2, which is talking about roughness parameters, and part 3, that it's talking about filters. So before we start with this slide, I want to mention that indeed this ISO 25178, it's giving the possibility of using a wide range of different filters, but the ones that we are going to explain in this presentation are the F, L, and S filters, which are the ones that are most commonly used. So after that explanation, here we have this sample in which we can find very different wavelengths inside of it. So actually we can separate these wavelengths in different groups. The first group would be system noise, in which we find the small frequencies, wavelengths, sorry, that are related to the noise of the instrument. Then we have the roughness wavelengths, which are the small sized wavelengths. Afterwards, we have the waviness, which are the middle-sized wavelengths inside of our sample. And finally, we have the form, which are those wavelengths that are so big that they are not fitting inside of the field of view that we are taking into consideration. So in order to separate those, we need to apply some filters. So we are going to apply F, L, and S filters to have these 4 groups. So let's start with the F operator, which is a nominal filter, and it's going to be able to remove the form out of the wavelengths that we have here. Then we have the L filter, which is a Gaussian filter, and it's a low pass filter, meaning that whenever we establish a value, those wavelengths that are bigger to that value, they are going to be removed. So indeed, this filter is going to remove the waviness. And finally, we have the S filter, which is pretty similar to the L filter, but it is a high pass filter. And what we are going to remove here is the super small wavelengths. So actually, this schematics, it's kind of explaining the same, but in a different way. So with an F operator, we are going to keep the system noise, the texture, and the waviness, and we are going to remove the form. While if we use an S filter, what we remove is the system noise, and we keep texture, waviness, and form. And finally, if we apply an L filter, what we keep is the system noise and the texture. So in order to understand better how these filters work, we're going to explain how a Gaussian filter works. So the S filter and the L filter, they are Gaussian filters. So in the case of the L filter, whenever we establish a value, which is going to be the nesting index, that means that that wavelength is going to be attenuated 50%. And that happens exactly the same whenever we establish a value on the S filter. So all these wavelengths that are smaller than the number that we have established here, they are going to be attenuated. So finally, what we are going to have is these small frequencies here that they are not going to be attenuated by any of those filters in this case. But also something that I want to mention, and I think it's pretty relevant, is to understand that the L filter is the most critical filter because it's going to be the one that is going to separate the population of waviness wavelengths and roughness wavelengths. So actually, this L filter, it's going to be different for each sample. Of course, we're going to have different L filter for a dental implant than for lenses. And actually, that's the reason why the ISO 25178 is not establishing any specific value for the L filter. So that means that it needs to be us to understand very well our sample and then apply the L filter that we need in our specific case. But even though the ISO doesn't give any established value, it does give some guidelines. So in here we can have a chart in which, depending on the magnification and the area, the ISO is recommending different nesting index. But those recommendations are taken into consideration in our Sensofar software, which is our analysis and visualization software. So from all the operators here that we can have in this software, we have this operator, the SA ISO 25178, in which we are able to calculate roughness. And actually, this operator it's going to take into consideration the lenses used in the area recorded, and by default, those are the default values that it's going to give us, which are the ones that follow the guidelines of the ISO 25178. And now let's go to the ISO parameters. So how do we obtain those ISO parameters? First of all, we need an instrument to do so, and our surface, of course. We're going to obtain the extracted surface, and to that surface, we're going to apply an S filter. So afterwards, we are going to obtain what is called the primary surface, and in here, we have three different paths. The first path would be to calculate the roughness parameters, which are called primary parameters. The second path would be to apply an F operator and have the SF surface. That means that we're going to only keep the wavelengths that are middle size or waviness. And we can calculate the roughness parameters out of that data set, which are going to be called waviness parameters. And finally, and the most common option, it's going to be the following one, which is applying an L filter and having an SL surface, which means that we are going to keep with those frequencies that are small. So from out of that data set, we are going to be able as well to calculate the roughness parameters. So we have defined the roughness parameters to be categorized in three different classes. So first of all, we have those parameters that are calculated from the dataset. Those ones would be height, spatial, and hybrid parameters. Then we have another ones that actually they are calculated out of motifs that we can identify inside the topography, and those are called feature parameters. And finally, we have the ones that are calculated from an Abbott-Firestone curve which actually it's an accumulative histogram, and we can calculate areal functional parameters and volumetric functional parameters. So we have a lot of different parameters that we can calculate out of a surface, but actually the ones that we are always asked for and they are most known are SA and SQ. That I'm pretty sure that you know, and actually they are means of height. So indeed, I believe I would say that these two parameters, they are really important, and indeed they are giving information about the surface. But from Sensofar, we encourage you to use more parameters in order to understand better your surface, because actually, if you have a look at these two surfaces, they have the same SA and SQ, and of course they are completely different. So again, we encourage you to try to calculate other parameters that for sure are going to give some important information about your surfaces. So let's go now to a practical case. We have been working with Antogir that they are doing long-term implantation in the spinal region. So what they wanted is to find a way to have a test which was going to characterize their samples of non-compliant and compliant. So for that, they were calculating SA, also calculating SZ, but actually the roughness parameter that was giving them that exact test and that possibility to have that test was this parameter, SMR, which is a functional parameter. So how this parameter works is the following. We are going to know how much material is going to be above 1 micron, which is the percentage of material above 1 micron. So with that, they established their cut tolerances, and they were able to just imaging, then calculating this parameter, and they would know which parts would be compliant and which ones would be non-compliant. So finally, yes, there's a lot of parameters, and yes, it can be difficult to find one that fits better to our surface. But in Sensofar, we have developed this new tool in our QA and QC tool, which is SensoPro. And actually, what this new capability of the software is allowing is that we can upload two different batch of surfaces, batch A and batch B. And SensoPro, considering as many roughness parameters as we want, it's going to calculate the statistical difference. So it's going to simplify a lot this procedure to find those parameters that it's going to separate our different surfaces. So for example, in this case, it's telling us that SDR is going to be the parameter that for sure it's completely different from one surface to the other surface. And that's the presentation. I hope you liked it, and we can start with the questions.